Hi, welcome to the module about regression and interpolation. Actually, this module is mostly about regression. The next module will cover interpolation, but we'll start out by introducing both of them, and then from the second unit on, focusing on regression. Let's start by going over what regression and interpolation are. They're basically function approximation using training data. What does that mean? Let's start with training data, which we'll think of as a collection of pairs of real numbers, an x and a corresponding y, and a finite number of these pairs, I equals 1 to n. Then there's regression and interpolation with this data. Regression aims to find a function from a specified class of functions, somewhat limiting usually, that best fits the data. Here's a mathematical statement of that. Minimize over all functions f from a specified class. Here bold f sub r is some set of functions that we're allowed to look over. And then the error is characterized as the sum of squares of differences between what the function evaluates to at xi as compared with what yi was. So we're trying to find a function that maps the x training data into the y training data, but the function is limited. We're only able to select functions from a specified class, and that's what f sub r denotes. We often do use this squared error criterion, a sum of the squares of the differences. We'll talk about other criteria, as well as a little discussion about why, at least in today's module, why the squared criterion is used. After carrying out this minimization, sum f is the best fit function. Let's denote that by f superscript r. Interpolation, on the other hand, tries to find a function also from a specified class of functions, most likely different than the regression class of functions, that exactly matches the data. It doesn't best fit the data, but it exactly matches it. In other words, find a function f from some class of functions, f sub I, with f of xi equal to yi for all the data points. So this function exactly matches the data. And let f superscript I denote one such interpolator. It'll be called an interpolator because it matches the data. That's what regression and interpolation are. The obtained function, either the optimal regression function or one of the interpolating functions, is often used for prediction. By that we mean, given another value of x, with y unknown, estimate or predict what's the corresponding value of y. The main points to get here are that regression tries to best fit the data, while interpolation tries to exactly match the data. In either case, the obtained function becomes a model for the process that is producing the data and is ultimately used for prediction concerning this data generating process. Even though we've just introduced the idea of regression and interpolation, let's look at a single training data set and some figures that represent regression and interpolation being carried out on this data set. In these four panels, the red dots represent the training data. The horizontal axis is x and the vertical axis is y. It's the same exact training data in all four panels. Remember that in both the procedures, regression and interpolation, the approximating function must be chosen from a specified class of functions. Let's look here in the regression panel. Remember that the red dots are the training data. The purple line here is a good fit drawn from the class of linear functions. Notice it's a straight line and it does a reasonable job of approximating the data, but it's of limited complexity and therefore it can't match the data perfectly. The green line is drawn from a larger class of functions. It includes functions that are linear and quadratic. We'll just call those quadratic functions. Generally, it does a better job at approximating the data. Still, though, it's just an approximation. It does not pass through the data points. Finally, the cyan line is a cubic function, and that does slightly better at approximating the training points. But in all cases, these functions, whose complexity is quite limited, linear, quadratic, or cubic, only are able to approximate the XY relationship between the training data. Interpolation also draws functions from specified function classes with the restriction that the functions must pass through the data. Up here in this upper right panel, the restriction on the function is that it is piecewise constant and not necessarily continuous. And sure enough, there is a piecewise constant function that passes through the data. Rather than restrict the interpolating functions to be piecewise constant, let's see what happens when they're allowed to be piecewise linear. Here, in the lower left-hand corner, is an interpolating function which is piecewise linear. Between each training point, y is a linear function of x, and at the training points, these functions all meet and agree. In this case, notice that there are abrupt jumps in the slopes on either side of a training point. The curve in the lower right-hand corner is something called a cubic spline. Between each training point is a cubic function, but the cubic functions are coupled in a manner such that the slopes and second derivatives have common values at each training point. We'll learn about all these three different methods of interpolation in the next module. So what are the two different perspectives? In regression, the measured data is thought to be inaccurate in some sort of random fashion. While the data may seem to exhibit some complex variability in the XY relationship, the belief is that that variability is not truly indicative of the underlying phenomena that produces the data, which is likely simpler. Therefore, the class of functions which is used to represent the phenomena should be no more complex than necessary. And then within this simple class of functions, regression produces an approximate fit to the data. Note that those four perspectives are consistent with what's shown in this upper left-hand corner. Fairly simple functions capturing the basic trend in the data, but not trying to fit all the complex variability that the data has. Let's contrast that with interpolation. In interpolation, we treat the measured data as completely accurate. Any complex variability in the data is thought to be truly indicative of the underlying phenomena that is producing the data. Therefore, the functional representation should pass through all the data points. They're all perfectly accurate. On the other hand, there's also no reason to expect any wild variability between data points. And finally, any knowledge about the phenomena that's producing the data, that is responsible for the relationship between x and y, should be used in order to set the smoothness requirements on the interpolating functions. It's possible that it doesn't make sense that the relationship between x and y would be piecewise constant with large discontinuities, or that it would have abrupt discontinuities in its derivative, and therefore one might be led to use a smoother interpolating function. Alternatively, the opposite could be true. It could be known that the phenomena is piecewise constant, and therefore the interpolating function should be chosen that way. So, any knowledge about what's producing the data should always be used in selecting the class of approximating functions. Let's test our understanding of these perspectives. I'm going to pose two problems, and we want to think through, for each of these problems, is it really a regression problem or an interpolation problem? And it's possible that there's not an absolutely correct answer for these. But the takeaway message is to learn some rules of thumb about when one method is preferable over another. Let's imagine that our task is to find an accurate and fast approximation to this very specific integral, the integral from 0 to r of e to the negative x to the 3/2 power times the tan inverse of x dx over the range of r from 0 to 5. The integral may have some very specific meaning in a certain application, and for some real-time application on a small microcontroller, There's no time to do the integral, so the integral needs to be represented approximately, but still, hopefully very accurately. So the data is pairs of r's and corresponding integrals, ri, fi, for some number of training points. That would be obtained by very careful numerical integration. Actually, we'll learn about numerical integration about 4 modules from now. In that sense, the data is repeatable and not subject to any appreciable error. Another problem involves the rebound velocity as a function of the impact velocity for a composite baseball bat and a baseball. Here, r is the rebound velocity as a function of v, the impact velocity. The data is several impact velocity, rebound velocity pairs that have been obtained from an experimental lab apparatus. Let's look at the top problem, the accurate fast approximation to the specific integral. Do you think that's a regression or an interpolation problem? And the rebound velocity as a function of the impact velocity for a specific composite baseball bat. Do you think that's a regression problem or an interpolation problem? Well, here's what I think. I think the first problem is interpolation. It makes sense that the fitting function should pass through the training points. The training points are nearly exact values. Remember, these were done by careful numerical integration. They're repeatable, and they're not really subject to any appreciable error. We're trying to find a function that exactly fits this data. I think the second problem is more of a regression problem. The experimental aspect hints at errors and probably some degree of non-repeatability in the training data due to uncontrolled or unknown factors. Here we might expect that even in several experiments that had the same impact velocity, vi, the measured rebound velocity might be different, again, due to these uncontrolled or unknown factors. Therefore, the data may have small, fluctuating complex variability, and it's not our intent to fit that variability, as it's most likely due to other effects.